Hi, my name is Patrick Cronin, and today I'd like to talk to you about our work charger surfing, exploiting a power line side channel for smartphone information leakage. Now, charger surfing is this idea that we're going to execute a shoulder surfing attack via the charger. And what we really mean by this is we're going to attempt to utilize the power signal from the charger to infer what is on the user's screen as they interact with it. Now, from an attack perspective, we really expect that many users are very comfortable plugging their devices into public charging ports. For example, at an airport or a hotel or a coffee shop, many users will freely plug their devices in without a second thought. We expect that attackers know this and might attempt to modify the port, somehow adding potentially a hidden voltage probe that can stream them the power trace as the user's device is charging. Then the attacker might utilize this power trace and perhaps some machine learning techniques to try to figure out what type of animations or interactions the user is having with the screen. Now, the threat of public charging has been studied a little bit in the past. In 2017, two independent research groups came up with this idea of potentially figuring out what app the users were using or maybe what websites they were currently browsing. Now, these are very coarse grained attacks that don't necessarily take into account the individual actions of the user, right? They're just looking at things like you went to Google or you went to Amazon. Our attack has more fine grained focus of potentially exactly what you might be typing into your phone at the time. Now, our intuition here is that we know the phone screen is going to refresh from left to right and top to bottom. We also know that as the user interacts with the screen, we're going to get nice animations. If we think about the lock screen where we focus most of this work, we know that there's a 3 by 3 grid with for the 1 through 9, and then a nice 0 at the bottom in almost all lock screens. So if we can figure out some form of locality, we might be able to figure out exactly what the user has pressed and what their passcode is. Now we know that every animation is going to lead to a different pixel color changing, and we know this is going to lead to some form of different energy cost. The next thing we have to prove is that there is some form of locality to these animations, and we do this by creating a preliminary testing app where we create a fully black screen and we flash white bars either in vertical positions or horizontal positions. And we classify those power traces, we average them together, or we want to see if we can at least detect difference. What we see is very interesting. If we look here, we can see that there are different power traces for the different locations on the screens. And this is for two different screen types, both an LCD and an OLED screen. And what's awesome here is we can see that there's a lot of separability to these signals. And that means that we can very likely to extract some form of locality information from them later on. Now, from a system design perspective, we have a couple things we need to solve. First, we need to acquire a raw signal, and let's talk about how we might do that. In a lab setting, we could very easily utilize an oscilloscope. We could just take that oscilloscope probe, stick it onto a very small resistance resistor that's been placed into the charging line, and we can record that power trace in nearly real time. And the next thing we want to do is look at kind of the button sequence detection and button isolation. And so we take a very low pass filtered image of our phone trace and we examine it just to see if we can identify where the button presses are. What we see is very nice, right? We can see this different screen off, screen on, enter the lock screen, and finally start to tap the pin code. What's very nice here is the pin code buttons each look very different from all these other actions. And so this leads us to believe that we can very easily separate them. Going a step further, we think about the fact that many users don't necessarily press the screen at exactly the same rate or like a metronome. So we start to look at how we might separate these button presses and classify them individually just so we can pass them to our network. So looking at a low pass filter of this signal, we look here and we can see that as we go through the signal, if we utilize some form of threshold, we can very easily detect the beginning of that button press and then utilize it to classify in the neural network. Finally, we now have, with all this information, we can start to begin to worry about what might our animation inferences look like, what kind of accuracy might we expect from the system. So in the system, we have two main goals. The first thing we want to demonstrate is that charger surfing is very effective across a wide range of phones with multiple users. And the next thing we want to do is demonstrate that it transfers across phones of the same model. The attacker isn't going to have your exact phone, so we need to make sure that he can train on his phone and test on your phone. So we have two kind of broad analytical thrusts here, one where we have 4 different phones and we look at a lot of feasibility studies, and then a more detailed analysis where we look at some of that cross-device testing. In the broad analysis, the first thing we want to do is just verify that we can achieve very good single button accuracy. We're not going to be able to do some form of pin code analysis if we can't at least figure out how to classify a single button accurately. So we gather a large amount of data from a number of different users, and we begin to process this. What we find is very interesting. We find that more users is actually far more important than more data. So as we begin to train for many users, we begin to see our accuracies greatly increase. And this is because users interact with the screen in different ways. Users might press more towards the left or more towards the right of a button, and that's going to cause different animations. As we gather more and more users, we begin to, really see the gamut of these animations, and now we're able to achieve very high accuracies. In the end, we had about a 98.7% accuracy with 5 training users. Next, we move on to a 4-digit passcode inferencing, and we look at this from 2 perspectives, our first trial accuracy and the 10th trial accuracy. We choose 10 trials as our bottom number because most phones don't lock you out after the first trial, but will really lock up or potentially erase themselves after 10 incorrect tries. We see about a 99.5% success rate after 10 trials, which is a very encouraging number. Remember, there are 10,000 possible combinations here, so this is much, much better than any type of random guess. Next, we look at a little bit of a feasibility analysis. Remember, up to this point, we're using an oscilloscope. We think, an oscilloscope is important because we need to have high frequency analysis and very stable analysis. But the question is, do we really need this? Or can we begin to decrease that frequency and potentially make our setup more stealthy? So we do a sampling frequency study, and we find that we can decrease our frequency all the way down to about 31.3 kilohertz before we really begin to see accuracy fall off. Now, 31.3 kilohertz is not that fast of a sampling rate, and we develop a low-cost attack to utilize this sampling rate. So we gather an ESP32 Wi-Fi enabled Bluetooth microcontroller, as well as an off-the-shelf analog to digital converter. Tying these two together costs less than $20, and we can create a very stealthy system that can stream very accurate data to our system for very low cost. Utilizing this low-cost system, we then start to enter a more detailed analysis. In our question here, we look at that kind of cross-device setting, some different configurations, and finally some defenses for this system. Now, our cross-device experiments, remember, the main thing we want to prove here is that this isn't independent, this is actually independent of the phone and doesn't depend on your exact phone. So if the attacker has an iPhone 8 Plus and is able to train the system, can his trained system attack your iPhone 8 Plus? And so we test this with 2 scenarios. We have 2 iPhone 6 Pluses and 2 iPhone 8 Pluses. The numbers we find here are very encouraging. Our single button accuracy is always above 99%, and even our 6-digit passcode values end above 96%. Remember, a 6-digit passcode now has 1 million possible values. So this is, again, far superior to any type of brute force random guessing. Finally, we look at kind of some attack effectiveness. And for attack effectiveness, we're really talking about what happens as we begin to change the conditions on the phone. It's not feasible for us to assume that you are going to have the same wallpaper or brightness settings as the attacker. However, if we can demonstrate that this doesn't really matter, that's a big win for our attack. What we see is exactly that. Across different brightnesses and different wallpapers, we see almost no drop off in accuracy. Our worst case number here is 97%, which again, really isn't that big of a fall off from our about 98% that we saw in the normal phone setting. Finally, we look at the countermeasures. And in the countermeasures, our big question is, can we stop this attack either hopefully in software, but at least in hardware? So looking from the software perspective, our idea is let's see if we can really gum up this system by adding a lot of extra noise via a live wallpaper. Now, with the live wallpaper, we're going to see continuous animation. So the question is, can the neural network identify the animations that matter from all these noisy animations? And the answer is yes. The neural network, when trained on a live wallpaper, was able to accurately inference any other samples we gave it as long as, again, we trained with the live wallpaper. So training with a live wallpaper teaches the network enough that it can test on any live wallpapers that we threw at it, and the system is completely not thwarted by live wallpapers. The next question is, all right, can we filter the power output potentially? We know that lowering the sampling rate is going to decrease the attack effectiveness. Perhaps we can filter the power output with a low pass filter, potentially an RC circuit within the charging circuitry. And we gave this a try. And what we found was, as expected, utilizing a low pass filter completely obliterates any signal that's useful to the neural network and charger surfing as a whole. And we're able to defend this system. So we would expect that, or recommend at least, that newer phones should have some form of charging circuitry that has a filter system built into it. I'd like to thank you so much for your time. And if you have any questions that aren't answered either by the slides or the paper, please feel free to reach out to us via that email there at the bottom of the slide. Thank you.